Welcome to Social Network Analysis. My name is Lada Adamic. I'm an associate professor at the University of Michigan. I'm affiliated with the School of Information, the Center for the Study of Complex Systems, and the Computer Science Department. What I'd like to show you in this course is what we can get out of modeling the world around us as networks. Now, the world is very complex, and once you represent it as a network, it may not really look any less complex, but indeed we can gain very useful insights. We can start to understand how information diffuses in social networks. We can also understand how resilient different infrastructure networks, such as roads or the electrical power grid, are to random or intentional failures. Here's one example I'd like to start with. These are hand-drawn networks made by the artist Mark Lombardi. He constructed them by poring over news articles in the 1980s and 1990s, making connections between political entities and different financial institutions and corporations. When you laid them out, you could see connections that might not otherwise be obvious just by reading the news articles one by one. Here is Michael Kimmelman, a columnist for the New York Times, commenting on having encountered a few folks from the Department of Homeland Security at an exhibit of Mark Lombardi's art. They found the work revelatory, not because the financial and political connections he mapped were new to them, but because Lombardi showed them an elegant way to array disparate information and make sense of things, which they thought might be useful to their security efforts. Now in this class, I'm not going to make you do hand-drawn network layouts, even though they're really hard to beat. But Mark Lombardi would spend days drawing these over and over until they were perfect. Instead, what we're going to be doing is using automated layout algorithms in software such as Gephi. Now here is a nice example of how automated layout algorithms make things very apparent. All they're doing is placing nodes that are connected through edges, close together, and other nodes are repelled. Actually, all nodes experience a repulsion force so that they're not all clumped together unless the ties bring them together. This is a data set of political blogs prior to the 2004 presidential election. This is who follows whom, who has whom on their blog roll. The liberals are colored in blue, the liberal blogs. The conservatives are colored red. Liberal to liberal ties are blue. Conservative to conservative are red. Liberal to conservative are purple. Conservative to liberal, orangish yellow. And what is apparent right away is that to some extent there's an echo chamber effect where liberals are primarily talking to liberals and conservatives are primarily talking to conservatives. And all I really had to do was run one layout algorithm. I did not have, in this case, although we did do this in our study, to even do any calculations for this pattern to be apparent. Now here is another example of a data set I had gathered. This is an organization, Hewlett-Packard Labs, so a bunch of researchers, and what we looked at was their email communication. If two people had exchanged at least a couple of emails back and forth over the period of a few months, they get a gray edge. I've overlaid here black edges which represent the formal organization, who reports to whom. Now what is immediately apparent from this visualization and what we confirmed in the study is that the email communication is more likely to occur between individuals who are closer together in the organizational hierarchy. But there are enough shortcuts across the organization that any two individuals are connected through a short number of hops, but the fact that those hops roughly follow the organizational hierarchy makes the email network navigable. So informal collaboration, getting the job done, it's reflected in this network. This network is my Facebook network. And what I've done here is I've used an automated community detection algorithm in addition to an automated layout algorithm to lay out my Facebook friends. And what the automated community detection algorithm did was it said, oh, there seem to be some people in your network who are tied together, and more so, they're connected more than they are to the rest of your network. And indeed, once you're working with this data, with an anonymized version of this data, you'll see that the different groups roughly correspond to different contexts in which I've met people, from school to work to outside of school and work activities. And this you can just tell without really knowing anything about my life. You can look at my network and understand quite a bit of it. The final network is one of ingredients, recipe ingredients. We analyzed tens of thousands of recipes to figure out which ingredients go well together. And then we made a network. In fact, we made several networks. And in this one, you can see that there are two main communities, one of savory ingredients and one of sweet ingredients. And actually at the very top, there's a smaller community, and you'll play with this data in time, that is the mixed drink community, where you have ingredients such as vodka and lime juice. So what I've shown you so far is that even just visualization can buy you a lot in understanding what the myriad of connections that we know are there can represent, but that might be rather invisible to us until we represent them as this network where they're all connected together. And this is where we're going to get the nice insight. I am going to be using maybe somewhat inconsistent terminology. So I may alternate between the words network and graph. Graph is the terminology where it all started in the field of mathematics, but I'm more likely to use the word network. For example, the new emerging field now is network science, and it doesn't make a network any less of a graph. It's just that you can use both terms. Similarly, I'm going to primarily use the words nodes and edges. However, nodes can also be referred to as vertices. If you're talking about sociological phenomenon, or you're talking to a sociologist, they might use the word actor. Similarly, for ties, a sociologist might say ties or relations. A physicist might talk about sites and bonds, although physicists who work on networks do say nodes and edges. And finally, in computer science, you might be talking about links, especially if you're talking about networks such as the World Wide Web. So we have a variety of terminology. It's very easy to get used to it, and all we're talking about in the end is that you have different entities and the connections between those entities, and that is what we're going to analyze. Let me get to the goals in this course. In addition to making pretty pictures, we need to really understand what the structure of a network is. So we're going to do some measurement, and in this measurement, we're going to look at whether nodes are connected through the network. We're going to look at how far apart they are in the network. How many hops does it take following these different connections? We're going to look at whether some nodes are more important than others due to their position in the network. And we're going to look at whether there are these communities in the network, that is, sets of nodes that are especially densely connected. We are not going to be satisfied just knowing that there's this structure. We want to know, where does the structure come from? What kinds of processes shape a network? So we're going to start with randomly generated networks, where you're just throwing edges at random and connecting different nodes. Then we're going to look at preferential attachment, where it's a phenomenon of rich get richer. As new edges are added, they're more likely to be added to the nodes that are already popular, in a sense. They already have many other edges. We're going to be looking at small world networks as well. So you might have processes such as, a friend of a friend is likely to be a friend because friends tend to introduce their friends to each other. And yet, any two people in the world are connected through a short number of hops. So recently, a Facebook study showed that any two people in the Facebook graph are connected with an average of 4.7 hops. we're going to see how certain processes might shape such small world structure. For example, how do small worlds arise out of optimization? For example, airline networks might be optimized to ferry passengers back and forth in a way that is efficient and doesn't cost the airlines much money. You might also have strategic network formation at the level of the individual. So the individual is getting something out of participating in the network, and so they may choose to connect to some nodes and not others. Okay, so we've described the network structure. We've figured out where that network structure comes from. And the final goal is to understand how that network structure now influences different processes occurring on the network in turn. So for example, we're going to learn how information diffusion is affected by the network structure. If any two people are connected through a short number of hops, does this mean that information will readily diffuse? Sometimes it's not information that's diffusing, but something that we don't want to diffuse, such as a virus. So how does the social network actually influence how quickly a virus is going to spread, and what immunization strategies can you use once you know what the structure of the network is? We may study the process, or we are going to study processes such as opinion formation. This can be kind of consensus that can be reached across the network as individuals continuously update their beliefs, or it may be just a single shot. You form your opinion only once, but it is influenced by what your friends think. We're also going to be looking at coordination and cooperation. If you have a certain task that you'd like to do, but it depends on inputs from the nodes that you're tied to, how quickly can you accomplish the task? And finally, we're going to look at resilience to attack. So if for some reason a certain subset of the nodes are removed from the network, can the network still function? Now, I've filled in the first 6 weeks, so you might be wondering what we're going to be doing in weeks 7 and 8. In week 7, we're going to look at cool and unusual applications of social network analysis. We're going to be looking at things such as recipe ingredient networks for predicting recipe ratings. We're going to be looking at the social networks of dolphins, and we're also going to look at economic development. So if you have the network of countries and the products that they produce, can you actually make predictions about which products the countries are going to produce in the future and how rapidly those countries are going to develop economically? In the final week, we're going to look at how social network analysis is used by companies such as Google, Facebook, LinkedIn, Twitter, Couchsurfing to enhance their product offerings. So what kind of social network analysis do they do? What kinds of research have they done? And how has this impacted and benefited the features of the social networks that they enable? So that's the outline of the course. In the next video, I'm going to dive right into it, and we're going to visualize some networks and see what it's all about.
Now, before we start using Gephi, let me tell you about the software tools that we will and won't be using. In this class, we'll be using Gephi for visualization and for calculating simple network metrics. We'll be using NetLogo to understand the dynamics that shape network formation and also to understand processes occurring on networks. And finally, for those of you doing programming assignments, we'll be using iGraph for more sophisticated, more flexible calculations. There are actually a lot of alternatives, and let me tell you about some of them, because once you know what capabilities you like, you can readily find them in other software that may be more well-suited to your projects. So there's the software package called Pajek, which means spider in Slovenian. It has been developed for a number of years. It's a very mature software package. It has very extensive functionality, which you access through drop-down menus. And the reason why we're not using it, even though I have used it when teaching this type of class in the past, is because it only works on the Windows platform, and some students have had trouble using Windows emulators on other systems. So I've just made the choice to switch over to platform independent software. However, Payek might be a very good choice. In addition, there is a book, a textbook called Exploratory Social Network Analysis with Payek, which guides you through many analyses that you can do with that software. We also will not be using UCINet, which again is fairly mature or very mature. It has extensive functionality, mostly focused around sociology. So I think until recently, UCINet did not really scale up to large networks. Unfortunately, it's also Windows only, and the license may cost you a couple of $100s if you're not a full-time student or somehow affiliated with a university. We also won't be using NodeXL. NodeXL is a relative newcomer. It's social network analysis neatly integrated into Excel. It's still, I think, very much in beta. It's being developed. However, it's free. And if you are already an Excel user, then this may be a very friendly way to do social network analysis. Again, it's actually Windows only. Only the Windows version of Excel supports NodeXL, and that's why we're not using it. If you're a programmer, there's an excellent alternative called NetworkX. It has extensive functionality, and it's actually built upon Fortran and C libraries, which are optimized to scale for very, very large matrices, and so you can do calculations for very large networks. It's on top of that, it's open source, so that's definitely something to consider if you have this background. There are many, many other alternatives. Most of them are in various phases of development. One very mature package is the social network analysis package for R. It has kind of statistics, heavy-duty functionality. For example, P-star models, which we won't even get into in this course, are supported in this social network analysis package. In addition, if you're interested, so P-star models are used to model networks as they evolve, to test hypotheses about what's driving edge formation. And if you're interested in visualizing networks over time with kind of an integrated P-star model functionality, there's the package Sonia that you can use for this purpose. Now let's get to our main task for this lecture, which is to work with Gephi. So what I'd like you to do is to download Gephi. It's free, it should work on any platform, and install it. Once you've installed it, download the data file dining.gephi from the Coursera folder for this lecture, and we can start to play. Now that you've downloaded Gephi and installed it, we can start to play with this dining.gephi data file. Now I've opened it recently, so it's shown in this helpful welcome screen, but perhaps you don't have that, so you can go to File, Open, and navigate to the directory where you've saved it, and then just double click to open it. And here we're waiting for it to load. And pretty soon it's going to tell us, for example, the number of nodes and edges. It's going to tell us there are 26 nodes and 52 edges. What kind of data is this? Well, this was data gathered in a girls' dormitory back, I think, in the 1940s, where the girls were asked to name their first and second choices for whom they would like to sit with at dinner. So this is the dining table partners data set. You can see a random layout here, and I've done this on purpose to demonstrate how even with such a small network as this one, a random layout can really obscure whatever insights you're trying to see. Now, Gephi helps a little bit, so here we can tell, for example, that this girl is relatively popular because lots of other girls have named her as their first or second choice. Now, if we want to know which girl exactly this is, what we do is we select this little arrow plus question mark. It's actually brings up an edit window over here, and now when we left click on this node, we find out that this girl's name is Ava, in addition to some other properties. We also may want to know the overall structure, so we can select a layout. And here I went to the layout panel, and I'm going to choose a layout. Force Atlas 2 is one of my favorites, but Yinfen Hu is also very fine. It turns out it doesn't matter too much when the network is this small. It's more with large networks that you run into visualization difficulties. So let's try Force Atlas 2, and I'm going to click on Run. There are all of these different parameters which you can tweak and play with that have to do with how the model is running. Essentially, all of these different layout algorithms want to place nodes that are linked close together, and ones that are not, it wants them to repel from each other. So we're going to say Run, and it ran. It's doing a little bit of spinning. Let's see if it'll actually spin into a good position. Oh, indeed. Very nice. Okay, let's stop it right there. And you may notice that now some nodes are out of view, so you can click this little magnifying glass that will center it on the graph, but it may end up looking a little bit too small. So I'm going to use the trackpad, or you can use your mouse wheel to just zoom in, and then I'm going to right click and drag and zoom in some more. And this, I think, shows off the layout of the girl's preferences a little bit more clearly. You may want to tweak things just a little bit. I'm going to select the hand to drag the node. Just here it wasn't quite clear who was picking whom, so maybe I'll just move it a little bit, right? So a little bit of minor adjustment is no big deal. If you're moving things around because you want them to look a certain way to prove some point, then I wouldn't do this. But just for us and wanting to see who exactly has picked whom, I think it's perfectly fine. Okay, some other things that you can do is you can change the color for all the nodes. So if we want them all to be red, and then I right click to choose the color, and then I left click to set them all to red. I may want to, yes, okay, these were a little overlapped, so we just want to avoid overlaps where we don't know whether an edge is incident on the node, or if the node is just over the edge and it's actually obscuring it. We can also adjust the size if these seem a little bit big. I'm going to right click on the size. Well, actually 1.0, that's already quite fine. I guess you could try a fraction of the size. Then I'm going to left click, and now they're tiny. So let's go back to 1.0 and set that. Oh, all right. Let's see, 5. Apparently it wasn't 5 before. Okay, there we go. So they were size 5. We may find this more informative if instead of having to click on this edit attribute, where we then click on individual nodes and find out, hey, this girl is Hazel, and this one is Maxine. This is where I'm seeing on all this info after I've selected the edit tool. Perhaps if we just show the labels for all the nodes, and so I'm going to click on this T down here that says show node labels. Oof, and they are way too big, so we're just going to try and scale them down a little bit. There we go. And we can go back to the layout and say label adjust. Try to move these around so that the labels don't overlap as much. And it's actually done it. I don't know if you could see it. It happened very quickly. And now all the labels are fairly visible. Another thing that we may want to do is to color the edges differently depending on whether this was a girl's first or second choice. So I'm going to go to the partition tab, click on it, I'm going to click on Edges, and I'm going to click this little reload, load the different partitions or actually characteristics of the edges that are discrete categories, and I'm going to click on Label. And this has whether it was first choice or second choice, so I'm going to click Apply. And now we see all of the second choices in blue and the first choices in red. And I'll stop here because we need to explain some additional concepts before we can use Gephi. Oh, but actually, let me show you. So we're right now in overview mode where we have all these different tools that we can use. We can also click on Data Laboratory. And in Data Laboratory, we have a spreadsheet of all of the node information, and if we click on edges, we have all of the edge information as well. And finally, in preview, we can preview the visualization that then we can export. So I'm going to click refresh now to see it. I should probably see the node label, so I'm going to click that and hit refresh. And then I'm going to unclick curved so that we get the arrows for the directionality of the edge. And perhaps I can also, change the background. In this case, maybe I want a blue background or something like that. Oof, no, not a blue background. Let's go back to white. And then if I wanted to export this, I would click this button down here, and I could choose whether to export it as a PDF or a PNG or an SVG file. I'm not going to do that right now because we have some more work to do. So I'm going to go back to Overview and stop here while we learn a few more concepts, and then we'll be back. Now we're ready to talk about the first few network metrics, but before we do, I wanted to just emphasize a few things about visualizations. Edward Tufte, who wrote a series of books on effective data visualization, said, "The success of a visualization is based on deep knowledge and care about the substance and the quality, relevance, and integrity of the content." In other words, you should know your network. You should know what you're visualizing in order to visualize it most effectively. Here are his 5 principles in the theory of graphic display. Above all else, show the data, maximize the data ink ratio within reason, erase non-data ink within reason, erase redundant data ink, and revise and edit. Now, this is a little bit different when we're talking about network visualizations. They're actually notoriously hard to interpret, and so we don't really have the luxury of very clear plots where we're deciding that we don't want this shading or that. But what we can take from this is that we don't necessarily want, 3D spinning visualizations, because all that's going to happen is we're going to see some balls with sticks sticking out of them that are flying around in space, and no one is going to get anything out of that. We should try and see what it is what is interesting in the data. Perhaps it's the geographical location of the nodes. Perhaps it's different communities. Can you bring out the communities with the visualization? Or maybe there's some especially significant nodes because of their position in the network. Can you highlight those nodes in some way? So that is basically what we are going to be after. Also, there are things that you want the automated network layer algorithms to do. The first I mentioned when we were talking about the Girls Dining Table Partners network, which was that you want to minimize edge crossing. So here is the same network visualized in 2 different ways, and this is better because it's minimizing edge crossings. Here you have an edge crossing, and so it looks a little bit less clear that this node actually doesn't have anything to do directly with these, that it's actually closer to this particular node, the one that it's linked to. Another thing that you'd like to have are uniform edge lengths. And here you just like the nodes that are connected to be about the same distance from each other. And this is better, for example, than this visualization where we may not know that this node is connected to these others, and here we may not even really see the edge between these two. Now there's an exception, which is when you have weighted networks, and that happens, for example, here you may want this node to be far away because actually these edge weights, which we'll talk about in just a sec, are fairly low. So you want to represent that distance between the nodes, and perhaps these two that are directly connected are very closely spaced. Maybe they're very tight. Maybe that bond is very strong, and so you do want them to be closer together. So it depends. Again, you want the network to effectively represent the data. Finally, one thing that I was doing was I was moving nodes away from edges that weren't incident on them. So here, for example, we might be confused thinking that this one node might be connected, have an edge to this node and another edge to this other node, but in fact, it doesn't have an edge to either of them. It was simply overlapping with that edge. So that is something that we like to avoid as well. And your ability to avoid such problems, of course, depends on the size and the density of the network. The smaller and the sparser the network, the more successfully layout algorithms can satisfy these conditions simultaneously for all nodes and edges. Now let's get to the metrics that we were going to discuss. We have the degree and the degree distribution, and then connected components. The degree is just going to tell us how many edges are incident on a node. So for example, we were talking about the girl Eva and how many other girls had named her or she had named. Now already you see that there is this property, directionality of the edge. And if an edge is directed, you can also call it an arc or a link. So for example, the relationship might be A likes B, A gave a gift to B, A is B's child. You can also have undirected edges. For example, A and B like each other. Of course, these relationships aren't always symmetric, as we saw in the dining table partners network and actually in many social networks, but sometimes the feelings are mutual, and so it can be treated as undirected. You can have A and B who are siblings, or A and B who have co-authored papers, for example. There are other kinds of edge attributes aside from the direction. So one of them is weight. For example, if you have the number of messages sent between two individuals, that could be the weight of that edge. And it makes sense, the more messages that two individuals send, the higher the weight you put on that edge. And of course, you can scale it differently. It could be linear or log weight. And depending on what your goal is, you're going to choose different and appropriate weights. You may also have ranking, just as we saw, the first and second choice of dining partner, but also maybe you're rating your friend from closest to least close. You may also have different types of edges. So some of your social ties are friends, some are coworkers, some are family. And finally, there may be properties that you're assigning to the edge that really depend on the rest of the network. And this we'll get into later, but some edges might be between, kind of acting as a bridge between two different areas of the network. And so they might have a special role, or what's called, the properties called betweenness. So we'll be calculating such properties, and edges, of course, can have any sort of property that you calculate on the graph. Going back to our schoolgirls and their choices, we see both that the edges are directed and that they have this ranking, the first and second choice. Of course, there may be a multitude of other things that you could add on there. For example, maybe some of the girls share a dorm room, etc. But in this data, we're just looking at first and second choices and the direction. The edge weights that you add can also be positive and negative weight. For example, a person trusting or distrusting another. Here I'm showing a fraction of the ePinions graph. Now this is a publicly available data set that we will be actually working with. And what it is ePinions is a website where users go and they rate products. Now, product ratings are, they depend on the individual who's giving the rating, and not everyone's opinion might be your own. So you have the option of saying whether you trust or distrust a particular individual, and this then influences whose ratings you're going to be shown and which products you are recommended. Now, in this fragment, you can see that there's a negative uh, community here of lots of people distrusting one another that's tied to a community that primarily trusts. And there are very interesting research questions around this. For example, what if you look at sets of 3 people, is it true that an enemy of an enemy is my friend or not? How does this play out in the data? How is this data represented internally? For example, if you're writing code or if you're just using some software, how is the software representing the network? The most basic way is with an adjacency matrix, but we'll also talk about edge lists and adjacency lists. Here is a very simple network of 5 nodes, and here is its adjacency matrix representation. And for example, if we look at node 1, node 1 is represented by this row and actually has no outgoing edges. However, it does have one incoming edge here from node 5. So let's see how this works. The entry in the matrix is 1 if node I has a directed edge to node j, and it's 0 otherwise if I and j don't share an edge. Usually, the diagonal of the matrix right here is 0 because usually you don't have self-loops. However, in some cases, you can have self-loops. For example, if the network represents who nominated whom for a certain office, well, individuals can nominate themselves, and you may very well want to have self-loops represented. And in general, you don't necessarily have that Aij, that entry, is equal to Aji. This would happen if the network is undirected. Well, it would be true in all cases if the network is undirected. That is, I linking to j always means that j links to I. Of course, in a directed network, you can have lots of instances of the edge being reciprocated. For example, when you look at friendship networks, a lot of friendships will tend to be reciprocated. We don't have to always use the full adjacency matrix. We can also use the edge list, and it's just a bit shorter. So you can have, instead of a bunch of zeros, you just list the things that are there. So 2 has an edge to 3, 2 has an edge to 4, etc. Now you can become even more compact than that. Especially you may want to do this if the network is very large and very sparse. Sparse means that out of all the possible people I could be friends with in this world, the billions of people, maybe I'm only friends with a few hundred. And so instead of having a billion zeros, I may want to just have an entry that says Lotta, and then it lists, first friend, second friend, third friend, etc. It's much more compact. So going back to our network of 5 nodes, we have an empty adjacency list for 1. For 2, we have that it has edges to 3 and 4, etc. Now, after we have done all of this nice representing, we can start to calculate degree. And degree just counts the number of incident edges on a node, and we may be interested in such things as who is the most popular. Can we count how many edges each node has and which one has the most edges? So again, it might matter whether your network is directed or not. Imagine that you have a network of who has loaned money to whom. If it's a loan network, then the in degree might represent how many different people did you loan money from. Out degree, on the other hand, might represent how many people did you lend money to. And so in that case, owing a lot of money, having high in degree may be less desirable than having high out degree, having people owe you. In other networks, you may not care about the directionality. So for example, if it's a friendship network and people are simply saying who their friends are, you may just want to treat the network as undirected and just count the degree. Or if you have a network of co-authors, again, you might just look at how many co-authors has a particular researcher had over the span of the last decade, for example. Now, you may be thinking, well, it's not all about how many friends you have or how popular you are. Um, there could be more important things, namely having to do with who your friends are. Maybe having a few quality friends or having a few well-connected friends might be more useful in some sense than having lots and lots of friends who are otherwise hermits. They don't interact with anyone else. So in week 3, we will consider other measures of centrality. But for now, we're just going to treat centrality, this importance of nodes, simply based on the immediate network neighborhood. So your direct neighbors in the network as opposed to the whole network. We can calculate these values from the adjacency matrix. For out degree, we're just summing the non-zero entries in a given row. So here, the third row tells us that node number 3 has 2 outgoing edges. So its out degree is 2. On the other hand, from the column, by summing the non-zero entries, we find that 3 has 1 incoming edge, and that is from node number 2. So its in degree is 2. Now, once we've calculated the degree of each node, whether it's in degree, out degree, or undirected degree, we can start to construct the degree sequence. And that is actually just the array that contains the degrees of each node. The degree sequence, in turn, can be folded into a degree distribution, where, for example, for this network, we can count one node that has 0 in degree. We have 4 nodes that have in degree 1, and 3 nodes that have in degree 2. And so then this is the distribution of degrees in the network. That is, it's fairly evenly distributed between the nodes. The next question we can ask is whether everything's connected. So here is a visualization of my Facebook network, and as you can see, there are several disconnected components. This can be quite significant. For example, if there is some vital information in one part of the network, if none of those individuals are talking to the rest of my network, of course they're linked through me, but let's imagine that I'm out of the picture, so it's just all my friends are on their own, they have to communicate, that there would be no way for that information to spread from that isolated component to the rest of the network. It may not be information, it could be a virus that's spreading some sort of disease, in which case you may very well want to be in one of these small components, because it means that whatever is spreading in here, you're actually safe from it, because you don't have any contact with anyone in the rest of the network. And so the overall connectivity of the network is actually fairly crucial. We want to know, is everyone reachable from everyone else for the most part, or is the network so sparse that most people have no way of contacting each other through intermediaries? Again, we're going to pay attention to whether the edges are directed or not. And if you do pay attention to that, you can calculate the strongly connected components. The strongly connected components are ones such that you can reach any node from any other node in the network by following directed ties. So for example, here with B, C, D, and E, you can start with any one of them and actually kind of move around here, right? So you can reach any one from any other one. However, A isn't a component off by itself, because even though you can reach A, say you start at C, you can go to D, you can go to E, you can go to A, but once you're at A, you can't go back. And the condition for the strongly connected component is that you can really go from any node to any other node within the strongly connected component. And here's another component that's completely disconnected. Here G and H are in the same strongly connected component, but again, even though from F you can reach G and H, you can't get back to F. So F is its own one node strongly connected component, while G and H are another strongly connected component. When you have an undirected network, or you choose to treat your directed network as undirected, then you can calculate the weakly connected components. And here now, because we're allowing this edge from E to A to be undirected, that means you can go from E to A, but you can also go from A to E. And now A, B, C, D, E are all in the same strongly connected component. And similarly, F, H, and G are in the weakly connected component, right? So this is a weakly connected component, and this is a weakly connected component. And if you're dealing with an undirected network, you can simply just say connected component. You don't always have to say weakly connected component. But if it's directed, you want to make the distinction. There is also the notion of a giant component, and it is the largest component, and if it encompasses a significant portion of the graph, it can be called a giant component. Now, this significant portion of the graph doesn't actually have to be the majority. Technically, the definition is that as the network gets infinitely large, the giant component is still going to occupy a finite fraction of it. So that's the technical definition, and practically speaking, if you observe pretty consistently under different conditions that your network has a largish component that occupies most of the network, then you can call it the giant component. And here's the giant component in this particular network. So just to recap, what we showed in this mini lecture is that networks can be represented as matrices or adjacency lists or edge lists. And we talked about useful network metrics that we're going to start out with. This is the degrees of the individual nodes and the degree distribution of the network overall. And then we talked about connected components, strongly connected components and weakly connected components in directed graphs where strongly connected components obey the directionality of the edge, and then the giant component, which arises in many networks and is the largest component in a graph that is not too sparse. And we'll talk about the giant component more when we talk about random graphs. Now that we've learned the two concepts of node degree and connected components, we could start to apply them immediately to the dining table's partner data set and see what insights we can get out of it. First, let's look at degree. Now we have some choices. This is a directed network, so we can look at in degree, out degree, or just undirected degree. Now why doesn't out degree make sense? Well, every girl is naming two other girls as her first and second choice, therefore all the nodes are going to have the same degree, same out degree. So we don't want out degree. In degree, on the other hand, is a lot more interesting because it's a reflection of popularity. If lots of other girls want to sit with you at the same table, well, that says something about how desirable you are in this girl's dorm. So let's look at that. The degree is calculated automatically, so you can just go straight to ranking and click on nodes and then choose in degree. Now we could color the nodes by in degree, but we're going to save color for the connected components. So let's instead look at size. It's this little diamond shape here. So I'm going to click on it. And we can choose the min and max size. I'm going to go, since these nodes are sized 5, I'm going to set the min size a little bit lower at 2 and the max size maybe twice that. There is this option called spline, and this just says, how does the size vary as this quantity of interest varies, in this case in degree. Since the inequality in popularity isn't that large and it's a relatively small network, this linear relationship is okay. However, if, for example, you were looking at a massive network, a directed one such as the web, and, well, you wouldn't be looking at the whole web, but say a subset of the web, and there could be one page that has 100,000 in links and many other pages that have one in link or no in links. And you wouldn't want a node that's 100,000 times bigger than other nodes. It would obscure your whole visualization. So in that case, you may want to do something like a log linear relationship, something like this. But for our purposes here, we're just going to go linear. So let's apply that. And voila, instantly we can see that some girls are more popular than others. Marion and Eva look like they're most popular, and Hilda doesn't seem to be doing too poorly either. Now, this is all visual, and if we want to actually look up the numbers, what is the in degree of each node, if we simply go to Data Laboratory, unfortunately, it doesn't populate the degree automatically. So we're going to go back to Overview, and we're going to ask it to calculate the average degree. Now, the average degree is 2, which we sort of knew because we have 52 edges and 26 nodes, so you can divide one by the other. So nothing surprising there. It has given us the degree distribution. We're actually interested in the in-degree distribution. And here you can see that, for example, 2 girls have in degree 6, but I don't know, 9 girls have in degree 2. So that's interesting in and of itself. However, what is super nice about this is that we can go back to Data Lab, and now we actually have the in degree. And clicking on top here, or this sorts lowest to highest, let's click again, and we have the 2 girls who have in degree 6, who are Marion and Eva. So that's a nice way of just getting at the numbers, and also if you're interested in the degree distribution, you can have a quick look like this. Of course, you can export this spreadsheet and analyze it further as well. So back to the overview. What we have is a picture where some girls are more popular than others, but we don't really know whether there are certain cliques or how information might flow. So I'm going to start out by asking the question, if someone had some piece of gossip, one particular girl, where could that gossip go? Or if you had a set of girls, would they all be able to hear gossip from everyone else? And this is precisely the question of who is in the same strongly connected component. Because if you're in the same strongly connected component with someone else, it means that anything that they find out can potentially make its way to you. So let's find the strongly connected components. So I'm going to go back to the Statistics tab. If you have filters instead, just make sure you click on Statistics. And I'm going to click on Connected Components. I'm going to say Run. And it's going to ask me if I want the strongly connected components, which I can get in a directed graph or not. And yes, I do in fact want the strongly connected components, because if you imagine the flow of information, if one girl says she'd like to sit with someone else, but that person doesn't want to sit with her, well, they may also not be willing to share information with her. So we really want to take into account the directionality of the edges. So I'm going to say OK, and it's telling me there's one weakly connected component, which just means if we treat the edges as undirected, everyone's connected directly or indirectly, which is true, right? We just have a single connected network. But it's telling me that there are actually 11 different strongly connected components, meaning that information wouldn't circulate throughout the network following directed edges. So we're going to close this, and now let's color the nodes by the strongly connected components. So I'm going to go to Partition here, and I want to partition the nodes, and I'm going to click Refresh to just get this new partition, which should be the strongly connected ID. And it's giving me some colors. Some of these seem a little bit similar, so let me just see. I'm going to right click and say randomize colors, and these look a little bit different, so I'm going to apply them. And I think this paints a very, very clear picture about the dynamics in this among this group of girls. So first of all, we have the purple cluster here, where all of these girls may be sharing information with each other, and they also include these two very popular girls, Marion and Eva. You see this one girl here, Alice, who names two girls in this cluster, but her color is actually different. She's in a strongly connected component all by herself because actually no one selected Alice as someone they wanted to sit with. We see this little component here of 3 nodes in blue. Betty, Hilda, and Hazel all had, well, Hazel had selected Hilda and vice versa, and Betty had selected Hilda and vice versa. So they form one strongly connected component. A similar dynamic with Jane, Mary, and Edna. And here is an example with Helen, Jean, and Robin. So here you actually have a closed triad, but what has happened is that Helen and Jean mutually chose each other, and then Jean chose Robin as her second choice, and then Robin chose Helen. So you can kind of circulate in here, and then Ada and Cora are their own strongly connected component because they chose each other. So this shows you a bit of the dynamic of girls in at earlier stages of their lives, but also there's some recent research showing that most social networks, when you're naming friends, tend to be fairly asymmetrical like this. And in this case, because it's a relatively small network, etc., even just looking at the strongly connected components without applying community detection algorithms, which is something that we're going to be doing later on, we can figure out a lot of the dynamic between the girls.